Something that we will use a little bit now and quite a bit later is the idea, and the fact really, that there's also heat transferred when a substance changes phase. So heat is also transferred during a phase change. But something that's really interesting that we'll see, that we'll also use, like I said, now and later, but the temperature remains constant. So all of the heat that is being absorbed or given off by the substance as it changes phase goes toward that phase change, and the actual temperature stays exactly the same. So we should do some definitions, and then I'm going to give you some values, and that's about it for this section. So in terms of phase change, so we are talking about things like vaporization, when something goes from a liquid to a gas, and condensation, when something goes from a gas to a liquid. And so you can see that these are the same process but reversed. So they will have the same magnitude of heat transferred, but it will have opposite signs. So an example of this is that for water at 100 degrees, this is a temperature dependent, so hopefully you can recognize that this is the boiling point of water. If we are doing vaporization, so liquid to a gas, the amount of heat, but this is at constant pressure, so we're going to call it enthalpy, the amount of heat that you have to put in to separate those molecules and get them far apart so that they're in the gaseous state, we call it the delta H of vaporization, and that is equal to a positive, because we have to put heat in, right? So the molecules have to absorb it, 40.7 kilojoules per mole. That's huge. It's a really big value. Which means that the opposite, so condensation, so the gas turning into a liquid, it's the exact same process, but it's reversed. So the molecules give off 40.7 kilojoules per mole of heat. So when they get close together, right, they're giving up some energy to go from a gas to a liquid, and the amount that they're giving up is 40.7 kilojoules per mole. So this is at 100 degrees Celsius, and the sample, whatever we're doing, remains at 100 degrees Celsius the whole time. So if you have a sample of water that's boiling, it is 100 degrees Celsius, and it stays 100 degrees Celsius until all of it has been converted into a gas. So this is one set of phase changes. For water, the other one that we care about, even though the name is going to feel a little bit weird and wrong, is fusion, which means melting. So this is melting as solid to a liquid compared to freezing, which is a liquid to a solid. So if we are at 0 degrees, so the freezing point for water, if we are doing H2O, let's say solid to H2O liquid, it's the delta H of fusion. And if you know, I use the VAP because it's still that process going back and forth between a liquid and a gas, and it's the same magnitude, so we just have to put the correct sign. The delta H for fusion, we have to put in 6.02 kilojoules per mole to get water to melt. So significantly less energy, but we don't need to pull those molecules completely apart. We just need to get them to move past each other a little bit more quickly. So the reverse process, melting, H2O, liquid. Well, did I say that right? Solid to liquid melting, you put in 6.02, liquid to solid. So freezing, the sample gives off, so negative 6.02 kilojoules per mole. So to get something to melt, we have to put in energy. When something freezes, it gives off energy. So these are the main phase changes that we care about for water, kind of the only ones that we deal with on a practical basis. There are other phase changes that you will see, and so everything is going to depend on the substance you're looking at and its actual freezing and melting points. So you'll need to look at those. So some other phase changes, you might see sublimation. And so sublimation is going from a solid directly to a gas. So this is what dry ice is doing. It is solid CO2 turning into CO2 as a gas. And then the opposite of that is deposition, which would be a gas turning into a solid, which is just how we create dry ice. So one thing you'll notice is that all of these are on a per mole unit. So one, it tells us that it depends on the amount that we have. And two, it gives us a clue about what the equation might look like to figure out how much heat needs to be put in or how much heat is given off when something freezes or melts or evaporates or condenses. So as an example, let's just do a quick one. And sometimes you will see that these come with equations and sometimes they don't. So what we are going to do is calculate the amount of heat, or it might occasionally say energy, but we're just going to specifically say heat required to convert 237 grams of ice let's not even say convert, right? Required to melt 237 grams of ice. And we have the delta H of fusion for ice, which is our 6.02 kilojoules per mole. And if we are melting, we're going from a solid to a liquid, we have to put energy in. This is going to be the positive version. So we have kilojoules per mole. The amount of heat required for this is just the number of moles of ice times the delta H of fusion. If you like having an equation, now we could also look at this as saying we have to put in 6.02 kilojoules for every 1 mole. Then we could just multiply it by the number of moles of ice that we have. Now, okay, they give us 237 grams, so we have to do a little bit of a conversion first. So, that's an issue, but it's not an insurmountable one. It's just an extra step in our calculation. So we could maybe say 237 grams of ice, which is just solid water, times 1 mole is 18.02 grams. That would put us in moles of ice, times 6.02 kilojoules for every 1 mole equals, That should be 79.3 kilojoules of heat that we have to put in. And just a reminder, right, what we're starting with, based on how this problem is labeled, we have solid water at 0 degrees Celsius, and then we put in 79.3 kilojoules of heat. What we have at the end is liquid water. At 0 degrees. It is the exact same temperature. So what this is going to make a difference for in your calculations is that if you wanted to take this solid water at 0 degrees and you wanted to turn it into liquid water at a different temperature, let's say we want to turn it into liquid water at 25 degrees. This requires 2 steps, right? Step 1, melt the ice so that you have liquid water at 0 degrees. Step 2, warm the water. So this is something to keep an eye out. When you have phase changes, you don't have a temperature change. So we need to handle each step individually.